Hello everyone. Today we come to tutorial 2, first year university physics, kinematics, including projectiles, part 2. We'll recall from the part 1 that kinematics is the description of motion in terms of velocity and acceleration. Okay, let's go to my notes. Now there's another important thing that I need to explain to you. Let me just show you the notes, and I'm going to explain it on the whiteboard. So let's look at these figures, and then the final statements. I'll leave this on the whiteboard on the screen so you can see them later, and then I'll come to the rules. So let me go to the whiteboard and explain all of this to you on the whiteboard. The point is a portion, and it is this. Normally people say that it's said that a deceleration is negative. So you put minus a, or if you have a number you put minus 2.734. You can either attach the minus sign to the number or the minus sign to the symbol. Either way, a negative acceleration, it is said, is a deceleration. This is not always true, so this statement is not accurate. Sometimes this is correct, sometimes it is not. And I'll show you this why this is so on the diagrams. But the basic reason that this is not always right is that the minus sign is also used to indicate the direction of acceleration. Remember, acceleration is a vector with a direction. And so the minus sign is often used when you're drawing coordinate axes to indicate the direction. So let me say this is not always true. Now let me show you why this statement is not generally true. Now to do this, I'm going to consider I'm going to try and draw my line straight, but it's a bit, especially the vertical ones, are a bit difficult to draw. Horizontal is a bit easier. But let me consider coordinate axes. Maybe I'll consider one dimension. To make it easy for you. Now, must define the positive and negative direction. This is the negative direction, this is the positive direction. Now, if my velocity is in the positive direction, and my acceleration plus is in the positive direction, then this is going to increase the velocity. So this is an acceleration. Now, if my velocity is in the positive direction and my acceleration is in the negative direction, my acceleration here is negative, and sure enough, it's acting in the direction opposite to the velocity, so it's slowing the object down. So this now is a deceleration. This then is an acceleration. Now, what about we have the velocity in the negative direction? And if I have my acceleration also in the negative direction. In this case, the negative acceleration is increasing the velocity. So this now is an acceleration, not a deceleration. You see, it's because the sign for deceleration should not be confused with the sign for the direction of the acceleration. And this is where the confusion arises. This is why the best thing to do, even the rule I gave you before is the correct rule, but it's may not be the best rule. The best rule is to draw your negative and positive directions. I'll give you some rules in a minute for getting the correct acceleration or deceleration and putting the correct sign. Now suppose I have this. I have the velocity in the negative direction, but I have the acceleration in the positive direction. This positive acceleration now slows the velocity down. So this positive acceleration is now a deceleration. So you can see why the statement that a negative acceleration is a deceleration is not always true. The exceptional case is here. Equally, a positive acceleration isn't an acceleration, but is a deceleration in some cases. Okay, so let's go back to the notes. Let me just make sure you've got the diagrams. These are the diagrams drawn neatly. These are the rules. I think this basically explains the rules, but the rules are stated here. So let me focus on here. Rule 2, first define the positive and negative directions. We're looking at one dimension to begin with. Specify the signs of the velocity and acceleration relative to the defined directions. This is what I did on the whiteboard for you. Alternatively, rule 3, if you choose the positive direction in the direction of the velocity, if you always choose the positive direction in the direction of the velocity, so you define your axes according to the direction of velocity such that the velocity is always pointing in the positive direction. In this case, and in this case alone, you can say the acceleration will always be positive, while the deceleration will always be negative. The best rule in my view is this one, where you define your coordinate axes and then you define the signs of your acceleration and your velocity accordingly. However, it's also correct to use this. So if you prefer and you understand things clearly, you can use rule 3, so you get the correct sign for acceleration and for deceleration, especially in your constant acceleration formula. Okay? In 2 dimensions, you can follow the same rules, but after you resolve your acceleration and your velocities in the horizontal and vertical directions, with the ordinary axes, vertical and horizontal, resolve your velocity and acceleration into horizontal and vertical components. Then you can apply the same rules as above in 1 dimension to each dimension separately. So you can apply it to the y direction separately and the x direction separately. It doesn't have to be horizontal and vertical. It can be any 2 orthogonal directions or perpendicular directions. When you use axes, by the way, it's explained here. If you're not very happy or very confident with axes, stick to 1 axis alone. Stick to the common one, plus x, plus y, minus x. So this is the common system, which I'll call coordinate system 1, which is the one I suggest you use if you're not confident. If you are comfortable with coordinate systems, then you may prefer to use this definition of directions. For example, in projectile problems, if you have an aeroplane and you're dropping an object from an aeroplane, it's sometimes easier to define your coordinate system like this. So if you're dropping an object from a high place, again, if you're not very comfortable with coordinate systems, then just use the common one, system 1, that I defined in the previous page. Otherwise, you can also use system 2 sometimes. In fact, you can define your coordinate system any way you want, as long as once you've defined it, you stick to the directions and attach vectors, components of vectors with the appropriate sign relative to the coordinate axes. We come now to the last topic, projectiles. I've given you some examples here of possible projectile motions. This is the common simple one, and this is the one where you can use your formulas for the trajectory. Y of x is a function of x. The time of flight, or the time to the maximum height. The time of flight, by the way, in other words, the time it takes from the starting position to the finishing position, is double the time it takes to reach the maximum. But these formulas can only apply to this special case. When you get these other variations, you can't use the derived formulae. Now, I've given you the derived formulae on page 27. So these are the possible types of projectile motions that you may come across in your tutorial questions. The projectile calculations. Essentially, I'll leave you to read this for yourselves, but I'll explain the methods on the whiteboard. So let me just leave my notes up for you. So you can read them for yourselves. You can stop the video and read it for yourselves. Now, the important starting point is resolving your initial velocity into the vertical and the horizontal components. And remember what I said, we take the magnitude of u, of the vector u. This is the hypotenuse, and you can remember the adjacent is always going to be cos. So you know that the adjacent ux is u cos theta. The opposite is always going to be sine. So you can write immediately uy equals u sine theta without having to go through cos theta equals adjacent of our hypotenuse, sine theta equals opposite of hypotenuse, etc., and then rearrange the formula. You try to get the size directly. Again, we can have this possibility or this possibility. Either way, you always begin by resolving your initial velocity into its horizontal and vertical components. Now, this is the important observation made by Newton in his famous book, Mathematica Principia. Important observations. Projectile motion can be resolved into vertical and horizontal motion. Hence, the constant acceleration formulae can be applied separately to the x and y motions. And we've shown this below. Because this is so important, I'm going to do this on the whiteboard for you. But where the projectile motion is not the simple case, you need to start from first principles. In fact, the formulas for the trajectory, for the range, and for the time of flight are derived exactly from these formulae. But when you have more general projectile motion, you need to start from first principles. In other words, start from here. Now, when I'm doing projectiles, I tend to use u for my initial velocities and v for my final velocities. So, in the case of the acceleration formulas for the x motion, they actually simplify because the acceleration ax is equal to 0. So let me do that on the whiteboard for you. Okay, let's look at some general projectile motion. Always begin by resolving the initial velocity into horizontal and vertical components. Let me suppose I have this trajectory. So the projectile is thrown from a particular height, y0, which is not 0. Let me just call it h. This one, the origin is at y equals 0. So x0 is 0. I'm going to choose x0 to be 0. And this is my y-axis, plus y, plus x. With this orientation, g is negative. I'm going to use a positive value for the letter, but when we substitute for the the value of the acceleration, we put the negative sign in. Right, the main thing is to consider my initial velocity. I'll call this magnitude to simplify things, just u. Then I resolve into the horizontal and vertical directions. Remember, resolving the easiest way, draw a rectangle with a vector as a diagonal, and the components are going to be the two sides of the rectangle, with all the tails of the vectors tied to the origin. So this is the ux component. I'm only going to consider the magnitude. The uy component, again, only the magnitude. We're normally given an angle theta. And notice that the initial velocity is tangent to the trajectory of the projectile. So my ux is given by u cos theta. My uy equals u sine theta. Remember, the adjacent is always going to be a cos. The opposite is always going to be a sine. Right, so let's separate all of this. All these problems are tackled by separating the x motion and the y motion and writing our constant acceleration formulae for each motion, horizontal and vertical. So let's start with x. X equals a half. Acceleration in the x direction. Initial velocity in the x direction. I'll use u for the initial velocities and v for the final velocities. And the initial position. My final velocity in the x direction is equal to axt plus my initial velocity in the x direction. And I also have my last formula, ax is my final velocity in the x direction minus my initial velocity squared in the x direction. Okay, those are my three formulae. Now similarly, I have the same formula in the y direction, but my acceleration now is g. Plus my initial height, or my initial y position, which is not necessarily finite. So which is not necessarily zero, but usually some finite number. Then my Vy, Gt plus Uy. And finally, my 2Gy equals Vy squared minus Uy squared. So those are my formula in the y direction. Now, as I mentioned, in the problems that you're going to encounter, x is going to be 0. I doubt you're going to come across a problem where ax is finite. If you do, then you have to use all of these formulas. But in most of your, in fact, I think nearly all of your problems, ax will be 0, so this thing greatly simplifies. So, for ax equals 0, formulae simplify. So my ax is 0, so my x becomes uxt plus x naught. Even though x naught is 0, I'm going to keep it in. You will substitute x naught equals 0 when you come to do the calculation. So I'll keep that as equation 1. And my equation 2, this is 0. So ux, sorry, let me do it the other way around. Vx equals ux. In other words, the final velocity in the x direction is equal to the initial velocity in the x direction. There's no acceleration, so velocity doesn't change. And similarly from this formula, when ax equal to 0, I get the same equation except it's squared. So these equations contain the same content. So I'm going to call them the same number. You can use either one. Obviously, this is not of much use. This one is. And these ones I'm going to need all three of these. So this is 3, 4, and 5. Which formula you use will depend on what data you're given in the question. But using these formulae and these formulae, you can solve many problems with projectile motion. In the special case where we're launched from the horizontal at ground level, then we land at ground level, you can use the formulae derived from these equations. I've listed them on page 27 of my notes. So let's go to my notes and have a look at them. Stop sharing. Okay, so these, there we go. One thing to notice, when I derived these formulae, I used minus g. So my minus sign is already taken into account. So here, in deriving this formula, I'm doing something different to what I would do in calculation. In calculations, I like to leave g positive and make the number the negative. So when I substitute the negative number. But in these formulae, I've done it the other way around, where I've attached the minus sign to g at the beginning and derived the formula. The reason I've done it differently is so that I don't get a minus sign here. It doesn't look nice, because I'll put a minus here, then I'll replace g by a minus, so it becomes plus again. I'll get the right answer, but the formulae don't look nice. And also, in your book Survey does it this way. So these formulas correspond to what you find in Survey. So in this formulae then, you substitute the positive value 9.81 meters per second. Okay, the derivation I will leave you to do for yourselves. But the first formula that I get from this derivation is a formula which tells me the position y for every position x. So I feed in x and I get the corresponding y value. So this is my first equation. My next equation gives me the time of flight. The time of flight is the time it takes from launch to landing. Now, the time to reach maximum height is half of the time of flight. So you can use the same formula for both things. So for the time of flight, you use the 2. For the time to reach maximum height, you delete the 2. The next formula is the range. The range is the distance, the overall distance the projectile travels. Again, we're always referring to this ground level and this specific trajectory. So this formula gives me the range. Again, the derivation I leave for you. Finally, the maximum height is given by this formula. Now, the maximum height reached is from there to there. So again, I'll leave you to derive. It's only a few steps. The majority of the steps are for the first formula. Okay, that concludes my revision notes. And let me say bye-bye until the next tutorial.